Okay, good morning, everyone. Today we're moving toward kind of a few more advanced topics. So far, we've looked at the resistive touchscreen as one design problem that we try to figure out. First, have that as a kind of a driving specification of what we want to do, and then kind of dive down through the process of understanding what needs to be built, doing a little bit of physics to understand how to translate something that we actually want built into some sort of a circuit model. And then we learned also about circuit elements and the basic circuit analysis techniques that will allow us to analyze that model once we create it. Right, so the two-step procedure is always going to be try to figure out what is the specification, how the materials that you have at hand can play to create that design, and then do some design abstraction into the simplest model possible that you can analyze while still preserving the key features that you want to observe. So that's the key set of things. And so we did that on the 1D resistive touch, 2D resistive touch, and then, hopefully in the homework, you also saw some problems with that. So today we're going to talk about an improved touchscreen. Screen. And previously we had this kind of structure, and this was a resistive touch. Two planes, and we said that if we measure them, if we alternate them, we will be able to find out the horizontal and the vertical by just changing where we measure while we apply the voltage to the opposite conductor. We kind of derived the whole set of things through voltage dividers that showed us that we can indeed measure the vertical first and then horizontal position of the finger. And that was the case if you pressed in any given location on the touch. But then we also saw in the homework that measuring simultaneous finger positions is limiting on this type of touch. Not to mention moves that you actually apply today regularly on your phones, like zoom out, like three-finger moves, or other types of movements where more touch points are involved. These kinds of things simply cannot be done. That's not the type of medium. So today we're going to look at a newer touchscreen that allows you to essentially have an arbitrary number of points touching the screen. So you could say that the goal to move from this design to this is arbitrary number of touch points. Right. So that would be one of the design goals. Another one is that, as we'll see shortly, this other type of screen that we're going to do will not require any squishing of any surfaces, which may be handy because you want your phones to be sturdy, the screens to be rigid so that it can be more reliable. And so what we ultimately want to do is kind of divide the screen into small areas. Small areas just because we want to increase the resolution of our touch. If I'm pointing somewhere, I want it to be a really small area of the screen. So we can call this one area like pixel. Right. And then what I ultimately want to do, and this is something that you often do as engineers, you start off with a desire of how something should work. And that needs to then translate into something that we call a specification, a design specification. It then tells me a little bit more precisely what is it actually I want to build, so it can give me some ideas how I'm going to go and build it. Right. So this pixel will be able to detect touch or no touch at the pixel level. So I want to be able to detect as many pixels that have been touched by either single finger, multiple fingers, or whatever on this whole screen. And even if that happens all at once, I want to be able to do it, right? So that's kind of the underlying wish. So to do that, we obviously need something else than resistive screens, right? We've already looked at what those look like and kind of derived the models for those. We know that cannot be done with resistive screens. So we're going to have to rely on a new physical component to try to leverage this. So I'm just going to first write it out, and we're going to define what that component is. And then what we're going to do is construct a set of models to understand the behavior of that component without diving into the physics. So at the circuit level. Once we understand how this new component composes itself in circuits, then we'll go back and understand a little bit of physics to try to understand how to assign a value to that component. And that will help us translate the physical dimensions of the touch screen, for example, or any other sensor into a circuit model. Right? So don't worry about, there's no need to know any physics again. Just like we started with the resistive touch, just defining the elements and how we analyze them, we're going to do the same thing with this new component. Okay? So this will be called capacitive touchscreen. Right. Okay. So let's first drive into the circuit model. Just going to define a capacitor. This is a symbol. Right. Okay, so this is capacitor. We usually mark it with the letter C, and a subscript would be like a number or a letter, depending how many of those we have in the circuit. Then, just like for any circuit element, we'll have I element, and we will have V element. Again, notice that we're obeying the passive sign convention, that the I element goes into the plus of a V element. So everything is kind of the same as we did previously. Right. Now, for elements, we said that there is an IV relationship for every circuit element that we introduce. Right? And that is what characterizes that element, because after all, those are the two variables that apply across the element. And so we're going to now define the IV element relationship. Right. And for capacitor, we're going to sort of derive it a little bit, because what holds in terms of V for a capacitor is not that I is somehow proportional to V, but it actually, the charge on the element is proportional to the V element. Okay. So, in other words, you can think of a capacitor as a bucket. Current is coming in, it's bringing some charge, and the amount of that charge in that bucket, in that storage, is proportional to the voltage across it. Okay, so we already know that Coulomb is a unit for charge. Voltage, for voltage, it's a volt, right? And then for capacitance, it's a farad. So let's just write it in farad. Okay, so from here, we can just do a simple derivation to link charge to current, right? We already know, so we already know that I element is equal to the dq element over dt, right? That's just a definition of current. Current is a certain amount of charge going through some cross-section in a certain amount of time, right? So that's all there is to this, right? But now we can apply this formula for charge on a capacitor to that current equation. And now, in most situations, the capacitance, this C term here, is just basically a constant. That's some physical property of that element. There will be cases later in your academic life where you see that capacitance can actually change based on the voltage itself, and then things become a little bit more complex. Or it could change as a function of time as well, in which case you cannot do this type of simplified derivative. But here we're going to assume that C is constant. And then we can just put it out of the derivative and just leave dV element dt. Constant over time. Okay? So we have now that I element is equal to C times dV element dt. So let me just write it once more because it's kind of a key result. So what we had for the resistor was that current was inversely proportional to the resistance and proportional to the voltage, right? I was equal to V over R, or V was equal to I times R. That was Ohm's law. In this case, the current is proportional to the derivative of the voltage, derivative in time. Right. So you could call this, and I'm just gonna, I know this is kind of against purists in circuits, but hopefully that's okay. You can sort of call this equation Ohm's law for a capacitor, right? I just want to kind of really start connecting these things together, right? It's not really, Ohm didn't really derive this law, but like we're just going to call it Ohm's law for a capacitor, right? So if we go and look at the IV curve, right? Now I'm going to draw I element not as a function of V element, but as because then I would have to figure out how the time plays into all this, right? But I'm going to draw it as a function of derivative of the V element. So how would that curve look like? Yes. Straight line through where? Okay, yeah, so straight line through the origin, and what's the slope? C. Okay. So if you're into analogies, right, you may notice that here, if you kind of think of a derivative of voltage as some small change in voltage, right, some small change in voltage, then this C sort of has properties of conductance, 1 over resistance, right? Because it links voltage directly to current, right? And so then if you remember our IV slopes for a resistor, it was 1 over R on the slope. So those are sort of some connections you can start making. If you're not into analogies, that's completely fine. You don't need to know any of that. So just apply the formula, and that's it, right? And actually what's beautiful about this formula is that you can use the same 7-step circuit analysis. So all I need to do to reuse all the knowledge that we have in circuit analysis is to replace in my equations the voltage of the element with a derivative of the voltage on the element. Everything else stays the same in the 7-step analysis. And we're going to do a few examples so you can see how this is actually completely okay thing to do. Any questions? Okay. If not, we're going to move on. So here's the first simple circuit. Okay. Okay. So this is our circuit. There's a current source and a capacitor. And so we're just going to go and apply the same exact 7-step procedure. I'm not going to label like every step, but we're just going to do one at a time. So what did we say we're going to do first? We need to label the reference node and label all the unknown potential nodes, right? So let's say this is a reference node. The only one other node in the circuit that's left is this at the top. So we're going to label it, again, U1. Right? Then we said, okay, arbitrarily label the currents. Okay, so I'll label the current here as I capacitor. Hopefully I don't need to label another current for this element. I'll just assume it's going up. So that's IS. Here, we're going to label voltage VC, which is following the passive sign convention on this IC. So everything is how we did it so far. Okay. Now, I'm going to write KCL. KCL for this top node. Can somebody tell me what that is? In terms of IS and IC. Yeah, IS equals IC. What comes into the node must come out of the node, right? Okay, so then we apply the element definition for C. What is that one? What is IC equal to? You flip the previous, yes? Okay. C times dVC dt. Notice this is exactly the same thing we just did here. Right? We're just defining the element. This is the equation that we're applying. Right? Okay? So the third thing we have is the voltage definition for voltage, what is VC. So U1 minus 0, that's the difference of these two potentials, equals VC. Right. So from these two, we can just do the quick substitution and figure out what's going on. So we replace IS in here, and then we replace U1 in here, and then we get IS equals CdU1 dt. Does that make sense? It's just arithmetic, basically, nothing else. Okay, now you have to kind of scratch your head a little bit for the calculus AB to kind of kick in and try to solve this. What we really want to do, remember, in circuit analysis, the goal is to find currents and to find potentials on the nodes. So I want to find what this U1 is, right? So Maybe I give you a minute to figure it out. No? Okay, maybe 30 seconds. Okay, how about 30 seconds? Talk to your neighbors. See if you can come up with a solution. Okay, anyone figured it out? Maybe not the... Yes. Can you speak up? Okay. Do you know the final thing? Okay. Okay, so let's go through it. Yes, it's the integral, right? So we have to figure out how to move things around and then get u1 as a function of t out of this. So, okay, so the first step, we can just multiply both sides by dt. So we're going to get is times dt equals c du1. Right? And then I can apply an integral. Right? So let's do that. Let's say from 0 to t is dt equals, and now I'm going to say from u1 of 0 to u1 of t, c du1. Right. And then I just solve the integral. Okay, so what's the solution of the left side? Yes, is times t minus 0, so that's is times t. Okay, equals, what's the solution on the right side? Okay, so here you have to remember that we said C is not a function of capacitance, and it's also not a function of voltage, right? That was kind of our definition early on. That's not always the case, by the way, but in all that we're going to do, we'll warn you if it's not the case, but in all that we're going to do nominally, that's the case. So I can actually write C times u1 of t minus u1 of 0. Right. And then I can just solve for u1 of t. So u1 of t will be equal to is over c times t plus u1 of 0. Okay. So if I was to draw u1 of t as a function of time, how does that look like? A line, okay, and a line, okay, starts at time 0 and starts where? Okay, so you're saying if we start at 0, there will be this component, u1 of 0 left. So you have to start from there, u1 of 0, and then there's a line. Okay, great. And so the slope of this line is is over c. So what this means is that the larger my current source is, the more rapidly I'm going to be charging up this capacitance, right? Because the current is proportional to the gradient of voltage, right? So the larger the current is, the larger my gradient of voltage will be. So the more rapidly I'll be charging up. And it's also C, the smaller the C is, the larger the voltage gradient will be as well, right? Or I'll be more rapidly charging that bucket, right, if the bucket is small. Okay, so one of the things to note here, is there an end to this charging? Like, time goes by, you come back 10 hours later, voltage keeps growing. What happens? In this analysis, nothing happens. The voltage can grow infinitely large, right? What happens in the lab if you try to do this? Yeah, you hear a pop. And a pop means that there was a breakdown in the capacitor. As we'll see later, capacitor has some insulating material, and just by building the voltage high for a fixed distance, you're actually increasing the size of the field, electric field, right? And because field is proportional to voltage, so then if you have a ginormous voltage, you have ginormous field, the field breaks the insulator. So there's some critical field for every insulator, even air. That's why we get lightning and things like that in nature, right? That's exactly when the field becomes too high, meaning that our natural capacitors like clouds and Earth become too charged up. Then there is this spike of lightning which breaks the air as an insulator. And so that same thing happens in capacitors at small scale if you try to charge them up continuously or increase the voltage on them beyond a certain limit, right? So try not to do that, especially if you're working with electrolytic capacitors. These can be very nasty. So, okay, just some safety tips. Or you can watch fun YouTube videos how people who are brave do it. Okay, so let's do another simple circuit. Okay, so here's the circuit. Again, we're just going to go through the 7-step procedure real quick. So we're assigning a 0 node, a U1 node. We can also just note from here that U1 minus 0, which is U1, equals Vs. Right. Hopefully by this time, people understand that. If not, ask me. And then on the other side, again, from voltage definition, this is the voltage element definition. This other one is just a voltage definition, that U1 minus 0 equals Vc, right? And then, again, we have IC equals CdVc dt. So it's the same as previously. So this is just capacitive element definition, right? So let's substitute some things here. Since U1 equals Vs and U1 equals Vc, right? Then from here, Vs equals Vc. Okay, so then we're going to substitute that in this third equation and get that this is CdVc dt equals C times dVs dt. And what is dVs dt? I'm hearing some right answers, but a little bit louder. 0, right? Why is it 0? Yeah, Vs is constant. That's the definition of the source. Right? So this is 0. So that means that IC equals 0. That's puzzling. So what this tells you is that whenever you have a constant voltage across a capacitor, the current of the capacitor is equal to 0. Right? And the reason is that by definition, the current on the capacitor is the slope of the voltage across the capacitor. So if the voltage is constant, the slope is 0. Right? Does that make sense? This is actually a really important thing that we're going to use throughout a lot of these capacitive circuits to make our life easier. Okay. So, in fact, that dives straight into another circuit. Simple circuit number 3. Okay, so this one may sound really scary, but hopefully figure it out. Okay? And I mean, we can also label here VR just for completeness. Right? Okay. So, who can tell me what is U1 in this circuit? U1 is this potential over here. It's equal to 0, right? Okay, why? Why is this voltage equal to 0? I have to admit it's a trick question, okay? Because it's not always equal to 0. It's only equal to 0 in some special... So, yes? Okay, so you're saying this will be 0 if the capacitor doesn't have any charge on it, right? Yeah. So, but if we look back at the definition of the capacitor, right? So let's see where I have that thingy. Well, even here, right? Q element is C times V element, right? So if this is 0, then the V element is 0, right? That's what you're saying. Yeah. So that would mean if this voltage is 0, then because VC equals to VR, then VR would also be 0. Okay, so that's a way to look at it. But how do you know that the charge on a capacitor is 0? Right? That's the question. I can take a capacitor that is pre-charged to some value and I hook it up in this circuit, right? And then what happens? Right. Yes? Yeah, it will discharge. Right? And we can write the whole set of equations. In fact, it has to do with first-order differential equations and stuff like that, because it relates the voltage on a capacitor, on a resistor, Ohm's law here, with the derivative of voltage on the other side. Right? So you will get a true first-order differential equation that you can solve, hopefully. We used to do it in this class, but then we said no. We're going to move it to 16B. So in 16B, you should be able to completely derive this and see what happens. What we're going to do here, instead, we're just going to say, okay, what happens at the end of the process? I can tell you now, based on everything that we've done so far, what happens at the end of the process. Right? And we call that end of the process, we call it steady state. Steady state. When voltages settle. Right? So, when voltages settle, meaning when voltages are constant. And I don't even need to know what value they are constant at. I just say, I assume the voltages are constant. Let me see how to solve the values. Right? So, I'm looking for U1 value when the capacitor voltage Vc is constant. So that's steady state. Right? So, what happens when capacitor voltage is constant? There's no current, right? So, let's look at this. IC equals C dVc dt. This is 0, right? Because Vc is constant. I don't even need to know what value. It's just 0, right? The current is just 0. So, that means that if IC equals to 0, that's a very valuable information. Now I can go solve the rest of the circuit. So let's say by KCL, how are IC and IR related to each other? KCL on node U1. Yes? You're almost there. Both are exiting the node. Yes. So they sum to 0. IC plus IR equals 0. Right? But I know that IC equals 0 from above. So that tells me that IR is also 0. So if IR equals 0, then by Ohm's law, on a resistor, VR equals IR times R. If this is 0, then VR is also 0. By voltage definition, we also have that U1 minus 0 equals to VR, right? That's just the difference of the potentials equals VR. We know that VR is 0, so therefore from here U1 equals 0. Does that make sense? Okay, so the bottom line in these types of circuits, when you see them, even if there is some voltage source or anything like that, when you're asked a question about what's happening in steady state, that means that there is constant voltage on the capacitor. You can assume that. From there, it goes that the capacitor current is equal to 0. And then once you have that information, what can you treat the capacitor as? What other element that we know has a current of 0? Open circuit, right? And then we said open circuits are really our friends. They simplify the circuit analysis by a great deal, right? There's just nothing there. So there's no current flowing, circuit gets simpler. Imagine you have a circuit with 10 capacitors, 3 resistors, and 1 voltage source. All of a sudden, these 10 capacitors disappear, right? They're open circuit. So you only have 3 resistors and a voltage source to solve. That's the type of analysis you can do now in 16A. The transient analysis, how do you get to the steady state? You will need to solve first-order differential equation. You'll get some exponential solution, etc., etc. So you'll do that later. Right. Okay. So let's use this analysis now to do some equivalent circuits. And why is that? Well, as you will see later when we talk about capacitor physics, capacitors rarely come alone. In real physical representations, there's usually a whole bunch of capacitors connected somehow together. From my finger right now, there's a lot of different capacitors going to all of these different objects, right? And so I need some way to be able to kind of create equivalent or jumble them all up into simpler circuit forms so that I can analyze, right? So one thing that we're going to do in 16A, in the context of our touch circuits, we're going to look at capacitor-only circuits. And the reason for that is that, remember the circuit we just did, right? If I have a resistor and a capacitor in the same circuit, and I want to truly express all the voltages and currents, not just in steady state, but overall, I have a mix of linear relationships between voltage and current, and linear relationships between derivative of voltage and current. Right? So if I was to create a system of equations, that system of equations would be first-order differential system of equations. Right? And then I would need to solve that. So it becomes a little bit yucky. People do it, and of course, if you do Laplace analysis and things like that, that will all become some linear system of equations. So you'll do that in the follow-on courses. But here, as we just said, if we assume only capacitance-only circuits, we can use a derivative of voltage in all these equations, and it's just linear equations, just like we did the 7-step procedure. So to do that, we had step 1, which was find TH or I Norton. Well, we said these are capacitance-only circuits. We're not even going to have sources, so this is gone. So there's no source. And step 2 would we want to be able to express the equivalent capacitance as I element over dV element dt. Right? That's just a definition of a capacitor. So what that really means is that I'll have some box of capacitors somehow connected together, and between any two terminals there will be I element and V element. Right? And I want to be able to represent this as C equivalent that has the same I element and V element, but I match not the V element, but match dV element over dt. So these two things are equivalent if currents are equivalent and derivatives of the voltage are equivalent. Okay, so just like we did for the R Thevenin and R Norton, there's two kind of tricks or two procedures we can apply. So we can either apply I test and measure dV test dt, or apply dV test dt and measure I test. In both cases, I can get CEQ as I test over dV test dt. Right. So in other words, I'll have some circuit, capacitors, I will apply I test, and then I'll measure dV test dt. And in B, I will apply, and I'm going to draw this here as a squiggly. This is kind of a changing voltage, dV test dt, and then I test. Okay? Okay, so let's do some examples. So make all this clear. Or clearer. Okay, so let's say I have a circuit like this. This is C1, this is C2. And I want to find an equivalent capacitance between these two terminals. Right? Like a capacitor that replaces this whole thing. Right? So, which of the two methods should I use? Like, I guess, method A or method B? That's the question. Should I apply current or should I apply voltage? Derivative. Yes. Okay. You say voltage derivative. Why is that? Okay, so you're saying that applying voltage here would be easier because both of these capacitors have the same voltage across them, right? So this is one node, this is another node, right? And in other words, they're by definition in parallel, right? So when they're in parallel, applying a voltage source is easier, right? So let's do that. We want our life to be easy, not hard. Okay, so this is dV test dt. This is going to be I test. So let's just go and label everything. So this is node U1. This is the reference node 0. We're going to label this as IC2, IC1. I'm going to label these voltages as VC1, VC2. Again, the other way around. VC1, VC2. This is all, again, passive sign convention and everything. So let's just write out what things are here. VC1 equals U1 minus 0, so that's just the voltage definition across. Same for VC2, and that's what you were saying, right? And we also know that U1 minus 0 equals to V test. Okay? We're applying a source here, so this is V test, right? So let's see what that means. That means that if I just do the variable substitution, is that from this one I can do a derivative. du1 dt equals dv test dt. From these two, I can relate them to the element definitions. Def. So IC1 equals C1 dVC1 dt. So that's C1 du1 dt. And IC2 equals C2 dVC2 dt. And that's C2 du1 dt. Well, from this one over here, I know that this is C1 dV test dt. And this is C2 dV test dt. Okay. And then finally I can write KCL for node U1. How does that one relate all the currents? Okay, so I test equals to IC1 plus IC2. Okay, and then we'll just substitute these two over here. So it's C1 dV test dt plus C2 dV test dt. So from here we can say that I test equals C1 plus C2 dV test dt. Or that C equivalent equals I test over dV test dt, and that's C1 plus C2. Whoa. Anyone alarmed by this result? No biggie? Isn't this weird? Why am I kind of acting like this? Yeah, it's kind of weird because what we just did with resistors, right? We had R1, R2 in series, for God's sake, right? And R equivalent was R1 plus R2. And look at the capacitors. They're in parallel, but the equivalent capacitance adds them up, right? So if you remember a little bit when we were doing the definition of capacitor, current versus derivative of voltage, capacitance was kind of the proportionality constant there, right? And we said, okay, it looks more like a conductance than a resistance, right? So then it sort of makes sense that it's kind of the dual of this topology. Okay, in fact, it will make even more sense when we do the next circuit. But these kinds of relationships are just interesting to kind of observe. So let's do another example to illustrate that point. Okay. So the question is, if capacitors in parallel were adding up to get the equivalent capacitance, what are the capacitors in series doing, right? What is that going to look like? So let's say we have C1 here, C2 here. And in this case, what is easier to do? Apply a voltage or current? Current, right? Why is that? Yeah, because these elements are in series. They have the definition of elements in series is that they get the same current through them, right? So then I don't have to solve for that current going around, right? So I'll just apply I test. And I'll look for the derivative of V test. Right. So by KCL, so I can label this like this is IC1, this is IC2, VC1, VC2, 0, U1, all that stuff. And so by KCL, hopefully this is easy. IC1 equals IC2 equals I test. Right? That's kind of the definition of things being in series. The elements. For each of the elements, we can write their own equations. So IC2 equals C2 dV C2 dt. IC1 C1 dV C1 dt. Right? And then we have the voltage definitions. And that is that VC2 is, okay, let's label this. Let's label this node U1, this is U2. So VC2 is equal to U2 minus 0. And then VC1 equals to U1 minus U2. Right. People see this? And then another one we have on this side is that VTest equals U1 minus 0, right? And that's 0. So all this is. Right. So now I'll just take all of these and just shove them in these element equations to get the derivatives, right? And so we can get that just for the VC2, we get that I test equals C2, and then VC2 is U2, right? So we're going to get du2 dt. And then we also get that from this one over here, let's say u1 minus du2 over dt. That's from this equation here. That's equal to I test over C1. So we're just replacing I test here, dividing by C1, get dvc1 dt. So this is dvc1 over dt. Okay, and now I have everything I need. So I have du1 over dt equals du2 over dt plus I test over C1. And I already have what du2 dt is. That's from here. That's I test over C2 plus I test over C1, right? This piece is coming from here. And then that finally tells me du1 over dt equals, if you look at here, that's actually dv test over dt. And that equals I test times 1 over C1 plus 1 over C2. And now we can apply our equivalence formula. So that's I test over dv test dt. Right? And that's 1 over C1 plus 1 over C2, or C1 C2 over C1 plus C2, or C1 parallel operator C2. So C equivalent equals C1 parallel with C2, where this is just a parallel mathematical operator. Yes? Why is... Oh, because I'm wrong. I made a mistake. Thank you. Or, sorry, I kind of made it like that just so you can catch me. Yeah, but VTest is really just U1 minus 0. So it's just U1. Okay, good. No one's confused by this? You are or you're not? Well, I kind of hate this notation actually, but it is what it is, and when you start writing really big expressions, you kind of, instead of writing this or even this, you really kind of grow on liking this because it's just so much easier to write. But keep in mind, why it's kind of a really tricky thing is we call this a parallel operator, right? But for capacitors, it applies to capacitors in series, right? So these are capacitors in series, right? So it's kind of weird, like a parallel operator, but applies to capacitors in series. So don't let that confuse you, right? Don't let the topology be confused with a mathematical operation. It just so happened that this parallel operator was applying to resistors in parallel. Right? That was kind of convenient to remember. But now, this parallel operator applies to capacitors in series. So just keep that in mind. Okay? Okay, so let's do another example. And actually, this one, hopefully, we can do with no math. We just write the solution. Wouldn't that be nice? Okay, and I want to express this as okay. So the question is, what is C equivalent? Okay, why don't you talk to your neighbors for a minute and see if you can come up with a formula. No I dv dt is nothing, just a formula of C's.
Sign convention, since the current goes up, why this part is negative, this part is positive?
Oh, because we're okay.
Okay. Anyone solved it? Okay. Okay, C1 parallel operator C2 plus C3. Okay, anyone got a different answer? Okay, should we go through it? Everyone understands where this came from? Yes? No, because actually that's a good question. The question was, is this commutative, right? So look at this over here, right? It is a completely commutative operator, right? Because addition and multiplication are both commutative, right? So I can do C2 parallel C1 is the same as C1 parallel C2. In fact, let's just write it down here. So this is the same as C2 plus C3 parallel operator C1. Right. Okay. Do people see how can you explain us how you got to this?
Well, if you look at C2 and C3, they are parallel, so they should be sum for intermediate equivalent with that C1 on top and intermediate equivalent on the bottom.
Okay, so you're saying this first. So let's call this C equivalent 1, right, was just C2 plus C3. And then what we have, when we go back to this circuit, we have C1 and this C equivalent 1. Now these two are in series, right, and these are our nodes A and B. Yeah, and now we apply the parallel operator between C1 and C equivalent 1. Does that make sense to everyone? So, if something's too big to conquer, what do? Divide it into small pieces, solve each piece. This is what engineers do really, really well. So, it's exactly what you should be doing on circuits like this. So, look at the circuits, see if you can apply these, break them up into these small equivalence pieces, and then put them all back together. Now, that's not always going to be possible. In fact, I think I had a teaser. Yeah, I can just actually sketch it out. So, okay, challenge circuit. Okay. Here's a challenge circuit. I'm not going to do it here. I can label these like C1, C2, C3, C4, C5. Right? For this one, and I'm putting this one down here for a reason, if you just try to be really quick about it and try concluding what is in series, what is in parallel, you may actually be wrong. Right? These are kind of classical bridge circuits that trip you up. So for this one, you likely will have to apply I test, V test, or dV test, dt, and then solve it. Right? And that's very doable. But you won't be able to just see what's in series, what's in parallel. So be careful. Right? Because sometimes you can just rush in and make a mistake. Whenever you're confused what's in series, what's in parallel, just use the I test, dV test, dt. Yes? Uh-huh. Oh, you mean not for this example, but for previous examples?
Well, why should we combine those results considering we use two different we apply I test for one?
You can apply either method. You can always apply either of the two methods. It's just that which one is arithmetically more convenient for you. Right? That's all. Even to this one, you can go ahead and apply both methods. But why bother where you can immediately kind of see what it is, right? Yeah, that's the point. Okay, so in the remaining 10 minutes, I sort of want to go back and relate some of these things to our physics. So we're just going to do a little bit. So that you have some tools. So we're going to define a capacitor as any two conductors separated by an insulator, right? Give me an example of an insulator. What is an insulator? Air, rubber, things like that. So ceramics also. So insulator cannot carry current. Right. Any two conductors could be two sheets of metal. Another example is surface of Earth and ionosphere. Right. That's two conductors. Lots of charge between these two, and we just said lightning is an example of when this dielectric or air insulator breaks, right? So here is one conductor, and let's say there's another conductor here. Right. So there's some capacitance there will be between these two conductors, right? So we're going to, and this is physical kind of model of this is the geometries. In circuits, we're just going to model it as a single component, C, right? And there will be a relationship between charge and voltage. This is kind of what we already defined. But now we're going to see kind of where that comes from, right? So what I'm going to do now is take two pieces of charge, a positive and negative, and then I'm going to move them onto these two conductors. So I take this positive charge, I move it here. I take the negative charge, I move it here. Notice that while I'm doing that, there's no opposition from the conductors. There's nothing on the conductor, so I can just take that charge, put it there. Once I do that, however, if I want to take the second piece of charge and I want to try to move it over here, then this charge that's already there tries to repel my positive charge. Positive charges repel each other. Same sign charges repel each other, right? Two negative charges cannot sit together. Two positive charges cannot sit together unless something's forcing them. Yes? That's right. Opposites attract. Yeah. So this is a little physics primer, right? So these two, once they are on the conductor, they will attract each other, just like you said, right? So they will stay there. But it takes some force to put them on, or some effort, right? Whenever there's effort involved, some energy is involved as well. I have to put in some energy to move these extra charges on once the previous charges are already on there, right? So remember that basically we defined the voltage as a chunk of energy that is required for moving a chunk of charge, right, from one point to another. So that's actually what's happening here. Moving the charge onto the conductor expended some energy, and that's now kind of, you invested some energy to move the charge onto the conductor. That is now contained in the capacitor, right? And is shown as this relationship, Q equals C times V. Right? In the notes, there's also a derivation based on this definition, right? That voltage is a chunk of energy dedicated for moving the charge, right? And so by combining these two, you can, again, practice calculus a little bit, and you'll figure out that the energy is equal to 1/2 CV squared. So that's the energy that we say is stored now in a capacitor simply because these charges are now populating the plates. Right? So in other words, and this is some analogy, we can say capacitor is a bucket for charge. Right? Now, how easy or hard is it going to be to put these extra charges on the conductor actually depends on the conductor's geometry. Just like physically when you're trying to add more stuff into a bucket, it will be easier or harder depending on the size of the bucket. Right? So same deal here. So the capacitor depends on one, geometry of the conductors, and two, material properties. Properties of the insulator. Because that determines the field. And remember, the field creates the force that kind of affects how charges interact with one another. Right? So we're going to label that material property as permittivity. And the units are farad per meter. Right? And let's say for vacuum, we usually put this zero sign here, so it's 885 picofarads per meter, where P is pico, is 10 to the minus 12. That's just a scaling. Right. So if we do the side view, it will look something like this. There's some distance d here. And in top view, there'll be some area, A. Right. And so based on these geometric properties, what we can write is that capacitance is proportional to area and inversely proportional to distance. And this sort of makes sense because what we're doing is saying, look, if the area is big, my bucket is big, and then putting in another increment of charge is actually not going to cause me that much effort, right? Because there's enough space for all these charges. And remember, effort equals voltage, right? So going back to this equation, if putting the same amount of charge gives me less voltage, then it's bigger capacitance, right? And so that's why if area is bigger, the capacitance is bigger. Right? And so the units, again, are farad. For this are meter square over meter. So unit check for permittivity is farad over meter. Okay? This is pretty much all you need to know about capacitor physics. We'll only be doing parallel plate capacitors. And so this is a parallel plate capacitor formula. And here's kind of where the material plays a role. In everything else, we just use our circuit models. So what you're going to get in your problems, usually, there's going to be some physical design from which you need to extract the capacitance. Once you extract the capacitance, you will also, from the physical design, have to extract the equivalent circuit model, meaning where are the capacitors, etc., and then apply some circuit analysis. And that's going to happen over and over and over again in this whole capacitance module. Okay, thanks.